All right, guys, we're going to continue on here with three more examples of integration of double integrals. This is pretty similar to the video we just did, where we're now going to integrate the region of 4 minus x squared minus 2y squared. And again, we're going to give bounds of x between 0 and 1 and y between 0 and 1 as well. So in this case, again, doesn't really matter where we start. You can start with the respect of x or respect of y. I'm going to go ahead in this problem and do it with respect to x. So I'm going to write down my integral from 0 to 1, and then my second integral again from 0 to 1. I'll write down my region, and then like I said, I'm going to start with the change of respect to x, and then with respect to y. So in previous videos, we've already talked about the fact that if I were to do this with respect to x, that both the 4 and the negative 2y is actually a constant. So when I do the integration from 0 to 1, I will do a 4x. I will do our boring old x cubed over 3 for the integration of x squared, and then negative 2y squared x. And then I'm going to evaluate this from 0 to 1 with my dy. Okay, so all I'm going to do here is start plugging in 1 to keep this pretty straightforward. So we have our 0 and we have our 1. I get a 4 minus 1/3 minus 2y squared dy. So remember, again, we don't plug the 1 into the y value at all. And then technically minus 0, right? Because they all have an x constant. So we would do the minus 0, but I'm not going to put that in there because you guys all know that. So we get 0 to 1, and then we're going to get 4 minus 1/3, which is basically going to be 12/3 minus 1/3, which is 11/3, minus 2y squared with respect to y. And then this is where, again, it gets super boring, but it's okay. We like boring. Sometimes we're going to integrate this now as 11/3 y minus 2y cubed over 3, evaluated from 0 to 1. And so our final answer here will be replacing the y with 1, and we get 11/3 minus 2/3, which gives us a answer of 9/3, which gives us an answer of 3. Okay, so you guys can see we're kind of getting the same old stuff here with the problem set. So one more time, I'm going to ask you guys to try example number 8. Pause video, do it, and I'll see you guys here in a second. All right, guys, so here is our solution. There's a couple of things that I would like to talk about here. So again, we have had the discussion about whether you should do it in terms of x or y. The reason why I chose x is because I like this u sub problem. I did not write this down, so I want to write it when you guys are with me here. So in order to solve the problem, remember y is just a constant. So if I make u equal to 1 plus x squared, I get the derivative of u is equal to 1 du. I get a 2x dx, and so the 2 is obviously where this 1/2 comes in from right here, right? We have to pull a 1/2 out of the problem. The other thing that I just want to friendly remind you guys about is that when you're doing u sub, if you decide to keep things in terms of u, that you need to change the bounds. And I know you all know very much right now how we change our bounds. This is what I call my bridge step, right? This bridges the u to the x. So when my x is equal to 1, right, then that means, when x is equal to 0, then my u is going to be 1. And then when x is equal to the square root of 3, square root of 3 squared is 3 plus 1 is going to give you 4. And so remember, as soon as you do that, this is all in terms of u now. You don't have to go back to x. Then we integrate the square root of u. Again, I'm going to pull the constant out right here before I start plugging my values in, because I much prefer the numbers to be outside to keep it simple. So integrate 7y. Again, plug in, and we get our answer of 7/2. All right, so look at that, see if you're okay with that. The one more thing I'm going to do on this video that I think is super cool is, well, if you see this problem right here, we could have done it a different way. So that wasn't horrible, but one thing that's actually really cool about this, and here's the notation for it. So the exact same problem that we do here is the fact that there's a property, as you guys can see right here, that if I can get like if I can do a product of the x's and then a product of the y's, I can actually integrate them separately. So what I mean by that, so I'm going to go ahead and write down that from x, I get 0 to the square root of 3, and I can take x square root of 1 plus x squared dx. And so I'm going to take this whole integral, and then what I can actually do with it is I can multiply that with our y values of 1 to 2, a very simple problem like so. So if I can get it where I have a product of an integral with all of x's and integral y, you can actually split this apart, which is exactly what you guys see right here. And so we can integrate this quite easily back in good old calculus, where we do make our u equal to 1 plus x squared. Our derivative will be equal to 2x dx. We have our 1/2 dx equaling to x dx. Again, when I change my bounds in this problem, then we're going to have, well, actually the 1/2 on the outside. So when x equals 0, u is equal to 1. When x equals the square root of 3, u is equal to 4. Again, I'm left with the square root of u du, which is going to be equal to 1/2 u to the 3/2 times 2/3. Evaluate it from 1 to 4. And when we keep doing the problem, we get 1/3. So 4, the square root of 4 is 2, which will be, and then 2 cubed is 8 minus 1. And I get that this becomes 7/3, right? And then here, this is the easiest one. We get this is y squared over 2. We're going to evaluate this from 1 to 2. So I've got myself a 1/2. I pull in a 4 minus 1, right? Y squared minus 1 squared, and I get this is going to be 3 over 2. And guess what happens when I multiply these two things together? I get the answer of 7 over 2. And as you guys can see, that is exactly the answer we got right here. So this can be applied to any double integral where you can get my entire integral in terms of a product of my variables. So I think that's actually pretty cool. So when you guys are trying these problems, take a look for a second and see if you can possibly do this. Now, if I did an x plus y over here, I couldn't do the problem. All right. So I think this is a really cool thing for us to look at. This work, I think, is a lot easier than it is the problem up here, but you can see we got the same answer for it. All right. So that's it for today. Have a good one, and I'll see you guys in the next video.